Okay, here is part 2 of applications of integrals. The second problem reads, the function above shows the function f, or the graph above shows the function f, with multiple sections such as the ones labeled r and s. F of x equals 3 sine to the second power of x plus 3.5. And then it says find the area of the region labeled r, and r is this region right here. So to find the area of r, we need to do an integration, but then we need to find the limits of integration, so that means that we need to find an intersection points, or find intersection points between f of x and line y equals 2, right? Alright, so we're going to plug this into our calculators, okay? And then we're trying to find our intersection points, okay? I'm using TI-84, so I think that's recommended by the College Board to use. Yeah, so if you're wondering which calculator to use, maybe consider TI-84. This is pretty good. Okay, and then one intersection point that I found was 0.597, and the other one that I found was, give me a second, the other one was 1.828. Okay, so these are the two intersection points. So area R equals intersection 0.597, 1.828. Okay, and then let's try to find the area from here. So we can see that f of x is above y equals 2. So this is our above function. So f of x minus 2 would be our answer. So I'm just going to write that directly. Sine 2 squared x plus 3.5, and then minus 2 would be, or dx would be our answer. And for this one, 0.799 for area of R. Alright, and then it says find the area of the region labeled S. So this one might be a little bit tricky. You might be lost, like I don't really know how to do this one. For this one, it's pretty interesting actually, because for this one you don't really know how to do it. You don't have to function in terms of y, so you can't use y equals 1 and y equals 2. So that means that you need to do some more algebraic thinking. So for this one, what we're going to do is that we're going to find the intersection points between y equals 1 and y equals 1 and the function f of x. So we're finding the area of this entire thing, this I guess r plus s, and then from that area we're gonna subtract the area of r that we found from a to get the area of s. Okay, so in that case, well, we already know the intersection points, right? We have we have 0 and 1, and then 2 and 1, so we know the limits of integration. So area of s equals limits of integration 0 to 2, and then the top function, which is f of x, is above y equals 1. So we're going to do f of x minus 1, right? And then minus area of r. Right? Okay, so for this one I got around 1.444. So this would be the area of S. It says write but do not solve the equation for the volume of the solid formed when S is revolved around the y-axis or x equals to 0. Okay, so this is when this part, right? S is revolved around like this. Okay, so it kind of forms a pudding shaped figure. It's like this. It's gonna be this shaped. The ends are going to be filled, but the inside is going to be blank. Okay, so that's the shape. But then since we have to use cylindrical shells for this one, you might be thinking, oh, the radius is in the x direction, right? So that's that, and then the height would be the perpendicular direction, which would be 2 minus 1, right? But then you might be thinking like 2 minus 1 is a little bit weird for me because it's not including like f of x, which is the function that we're talking about. And then like the integral is supposed to be influenced by this f of x because the graph is f of x. So you might be thinking it's a little bit weird. So I'm going to show you a different way. So I don't think that is the right way. So instead of focusing just on s, we're going to focus on the entire shape one more time from r to s, okay? And if you revolve this whole thing across the y-axis, then you're going to have a very similar shape, but it's going to have a little bit of a different height, right? It's going to be like this, okay? So it's bigger, basically. So what you're going to do is you're going to find the volume of this entire area, and then you're going to subtract the volume found by revolving the area of R across the y-axis to actually find the area or the volume of S revolved around the y. Okay, so first we're going to get the volume of the entire thing, which would be 0 to 2 in terms of x. 0 to 2, and then x is still the same because it's an axis revolution, and then our height would be f of x minus 1, right? The height is 1. Minus 1, and then dx, so that would be our entire thing, and then minus, we have our r of x, which would be 2 pi, from, again, the intervals are 0.597 and then 1.828. And then from here, we're going to do x again, because this is also an axis revolution, and then we have f of x minus 2, right? F of x minus 2, minus 2, and then dx. So if you plug this into the calculator, I think you should be getting an answer of around 11.382, right? So our answer would be 11.382. Of S. Okay, and then when you're actually doing exams, I think they expect you to like write what these represent. So you have to be like Vs equals V of Rs minus V of R, right? Right, and then you have to, yeah, that's basically it, I think. Yeah. Alright, and then part D says write but do not solve an equation for the volume of the solid formed when R is revolved around the x-axis. Yeah, I know for the part C it also said don't solve. I just solved don't solve. And then write but do not solve. Okay. And R is revolved around the x-axis. Okay, and then we have R, and then when this is revolved around the x-axis, it's probably going to form something like this. Okay. So in this situation, I think S is being disregarded. Yeah, and then this length is supposed to be the same as this length. I think the drawing is a little bit out of proportion. Yeah. Alright, and then it says when it's revolved on the x-axis, this means y equals 0. So the terms match. So it's not cylindrical shells that we need to use. I think it's probably going to be washers because the middle part is blank. Okay, so starting off, we have our integral area of R equals integral from 0 to 0.597 and then 0.828, and then we also have pi outside. Let's find our radius. Our radius, I think, would be so the outside function right now from the x-axis would be f of x. So it'll be f of x squared, and then minus the inside function, which would be here, right? The inside function would just be 2. So 2 squared, and then entire thing dx. This would mean pi 0.597, 1.828, and then if we have to, okay, I'm just going to say f of x minus 4, okay, and then dx would be our answer. It says that R is the base of a solid with semicircle cross-sections perpendicular to the x-axis. Write but do not solve an equation for the volume of the solid. So we have this one right here. Let's just say that we have these circles, and these circles are also 3D, so do not worry. Let me try to, yeah, these are 3D circles, right, all along the way. I'm just gonna draw a few to give you some ideas, okay? And then these like really thin strips of, or like pieces of the semicircles will form a 3D, I guess, model, or like a 3D function. And then let's first see the area of a semicircle, which would be pi r squared over 2, right? And then for the volume of the solid created by R would be the area of the cross section, which is like the semicircle, and then that integral, and then dx, because the dx represents the thickness of each of these strips. And then by doing the integral, we're just basically combining like the thickness times the area of the semicircle for each of these strips along the way of these intersections. Okay, so first we're going to set the interval, which would be 0.597 and then 1.828, and then 597, 1.828. And then let's try to incorporate the area function. But then what is R here? R here would actually be this much, right? So let's just first find the diameter. Diameter would be equal to f of x, right? F of x minus 2 would be the diameter, right? From here to here would be our diameter. Here to here, here to here, here to here, which would all be f of x minus 2, right? And then f of x minus 2 over 2 would be our radius, right? So, okay, and then because the area is pi r squared over 2, we are going to square the radius. We're going to put the pi outside, pi over 2 outside. Radius squared would be f of x over 2 squared over 4, and then dx. We're going to put the 4 outside too, so 8 over pi, 0.597, 1.828, and then radius minus 2, radius squared, which would be 3 sine squared minus 2, and then everything squared dx. So this would be our integral function for the solid with base in R, and then with cross sections perpendicular to the x-axis as semicircles. That's it. Thank you.